Okay, not too bad. Okay, most of this will be review for you, but hopefully you'll get something out of it. The rest of you, good. You'll find out about it. Squeak or Pharaoh? Oh, good, okay. And VisualWorks, Visual or VA, other people? Okay, some of those. Okay, very good. All right, so the real fundamental question here is, what is GemStone S? That we're going to be answering today. So the first thing is, it's a Smalltalk implementation. Like other implementations, like Squeak, like Pharaoh, we have a virtual machine, which is our own virtual machine. And we have a class library that goes along with that, so it's a complete implementation. And for most things, it's, well, you know, a Smalltalk implementation is kind of a Smalltalk implementation. There's a lot of things in common with all the ones that most of you are familiar with. So I'm mostly not going to be talking about those things today. I'm going to be talking about the things about GemStone that are different, because that's going to save a lot of time and hopefully bore you somewhat less. So the biggest thing that is different about GemStone S from things like Squeak, Pharaoh, VisualWorks is that it's designed to be a server-side Smalltalk. And you know, then you ask, well, what does it mean to be a server-side Smalltalk? Well, there's a couple of things that really stand out. One is that it's headless. It has no graphical user interface, and that it's designed to be multi-user. And we're going to talk in a little more depth about what each one of those means. Okay, so there's no graphical user interface. So there's no mouse input. There's no display on the screen. Well, then how do you use it? Well, you know, there's a couple of things. If you want to deploy an application, you know, in production, then you've got a couple of options. One is that you can do a web application and have the GemStone Smalltalk serve up the web pages for you, or work through a web server such as Apache, through FastCGI or some such thing to get your web application out there using the Seaside framework or AIDA, or there's a couple of other things that have been used with GemStone, some of which you'll be hearing about later in the conference from James and from Dale. You can also do desktop application deployment using a product that we have called GemBuilder for Smalltalk, or GBS. And this is a product that runs on a VisualWorks or VA Smalltalk client, desktop client, and communicates with a GemStone S Smalltalk server. And there are, it's basically, GBS is basically a special purpose distributed object system that can, you can make remote message sends from the client to the server, or from the server to the client. You can also have objects that are replicated between the server and the client, where the objects are logically the same object, but live in the object space of the server Smalltalk and live in the object space of the client Smalltalk, and the state of those objects is automatically synchronized. If you change it on the client, it also changes on the server, and vice versa. Now, for development tools, that's the other thing that's missing in a headless Smalltalk, is you don't have browsers and that sort of thing that run directly in the server Smalltalk. So there's several options you've got there. GemBuilder for Smalltalk, besides the replication and object message forwarding capabilities, comes with a suite of tools, browsers, inspectors, debugger, that sort of thing. There's also a set of tools that we've written that run in Pharaoh or Squeak, called the Gem tools, that also have those tools in them. And we will be hearing later in this conference from James about web tools, which is a newer framework that has some tools, and an experimental framework that Dale is working on, that he will be talking about on Saturday, called Toad, for the object development environment. So that's kind of the summary of the headlessness. Now, multi-user is a little more complicated. So in a typical traditional Smalltalk, the way it operates is that all of your objects are in memory, and you send messages to them, they execute their behavior, they change their state, and then at some point you take a snapshot, which creates an image file on disk, which is basically the state of all of those objects at that moment in time. And then when you want to, sometime later, you can start up a virtual machine and it will read that image file off of disk, recreate all of those objects in memory, and continue executing from where it left off. And just keep going. So you can save the state of all of your objects persistently. But this is essentially a single user model of persistence, because if you have multiple people, certainly multiple people can take the same image and start a VM from it and make their own modifications to the objects. But if they all try to save their images to the same exact file, then whoever saves the file last is going to get their changes in and everyone else's changes will be lost. So, so that is a single user model. So we want to do a multi-user thing. And what you might want for multi-user is that if multiple people started with the same image and had all these objects, and you wanted to all make changes to them and then save the changes, you might want your changes to be merged somehow with the changes that someone else made. And that's exactly what GemStone S does. And we do that through the mechanism of transactions. And transactions are familiar to many of us from, excuse me, the microphone does not reach to my water. And I put the water over there so I don't spill it. Transactions are familiar to many of us from working with databases, relational databases, kinds of things, similar concept. So there's several messages that you can send to manipulate transactions in GemStone. You send begin transaction, and that updates your view of the repository, or which is the entire object space of persistent objects, and puts you into a transaction. Now the view is, when that updates the view, that means that the latest thing that was committed by anyone else, all of those changes are now, that's the state of the world, as it were, that you see at that point. And then you can do your work in your own session, and you can make changes to objects and things, and you can see those changes. But you won't be seeing the changes of anyone else that anyone else is making at that point, because you're in a different transaction than they are. And even if they commit their transaction, you won't see their changes yet. The database people call this read consistency. In an SQL database, read consistency usually lasts by default. There's usually some options, but by default it lasts the length of one one SQL statement. So if you do like a select statement or an update statement, usually a select statement, a query, then you're guaranteed that your view of the state of the database is consistent for the length it times to execute that one query. So if someone else commits in the middle of the query, you're not going to get part of what they committed. You're going to get either all of what they committed or you're going to get none of what they committed. But usually it's only for that one query. If you do one query and then you immediately do another query in a separate SQL statement, then you may see a different result because somebody else may have committed it in between. With GemStone, we offer read consistency until you explicitly say otherwise. So you can go on computing and sending messages and changing the state of objects, and you won't see anyone else's changes until you execute one of these messages that I've got on this screen, begin, abort, or commit of a transaction. So begin just updates your view to the latest view. Now abort transaction, if for some reason you want to throw away any of the changes that you've got, if you've made any changes, abort transaction will discard all of those changes that you've made, and then it will also update your view to the latest committed view of the repository. If you say commit transaction, it will take any work you've done, and it will merge those changes with the changes that anyone else has committed during the time that your transaction has been active, since you did a begin transaction or an abort transaction or a commit transaction. It will merge those changes in with theirs, make the new state of the repository the merged state of all those changes. And then it will update your view to that new merged state. So anything that you look at, you'll see other people's changes now at that point as well as your own. So that's not too bad, but of course it's not ever quite as simple as it might seem. It is, of course, possible to have conflicts. Generally we use what is called optimistic concurrency, which is you're optimistic, you hope that most of the time, you believe that most of the time there won't be a conflict, so you assume there isn't going to be one, and if there is one, then you're going to detect it and recover from it. First we have to ask, well, what is a conflict? And when you're merging changes together, it's somewhat like in a source control system like a CVS or SVN. If two people modify completely different source code files, then that's clearly not a conflict. At least those systems don't think it's a conflict. You can make code that breaks by changing two different files, and the system won't detect it, and you will commit successfully anyway. And often in a system like SVN, you can change, two different people can concurrently change two different parts of the same source code file, and it will manage to merge those together successfully and not detect it as a conflict. But if you change lines that are close to each other or the same line of code, it will say, no, you've got a conflict there, you've got to resolve that. We're not going to let you commit that change without doing something about it. In GemStone S, it's the same thing. Now, since the objects are typically fairly small and fine-grained things, the unit of concurrency that we have by default is the object. So generally, if the set of objects that you've changed, if no one else has changed any of those particular objects, then it's usually not a conflict. And we'll just make the changes to those objects and go on. But by default, if you change the same objects, then that's a conflict. And there's some exceptions to that we'll see in just a minute. So if you do have a conflict, then there are messages that you can send to inquire about, well, what objects was it that caused the conflict? And then you can abort your transaction, and then it's application dependent as to what you need to do to recover from that. If it was a bank balance, for instance, that someone else changed the bank balance and you also need to change the bank balance, then clearly you're not just going to abort and write the same value that you were going to do. If you were going to deduct 100 pesos from the bank account, then you would need to take the new balance and deduct 100 pesos from that, rather than deducting it from the original amount that you had computed. In cases where there may be a lot of conflict and it doesn't pay to be optimistic, there is also the option of pessimistic concurrency, where you put a lock on an object before you modify it, which prevents anyone else from modifying it while you hold the lock. That's usually less used in GemStone, but it is an option. So logical versus physical conflicts, we refer to modifying the same object as a physical conflict, but logical conflict is a semantic conflict. So in some cases, like if someone in the personnel department of a corporation is modifying an employee object, and one person modifies the address because the employee has moved to a different location, and another employee is giving that, or another HR person is giving that employee a raise and changing their salary, that's not a logical conflict. But it could be changing the same object, so we would detect that as a physical conflict. And there are ways of handling those things so that those can be allowed and recovered from. Typically those are application dependent. But in the case of collection objects, sets, for instance, there's a lot of things that aren't logical conflicts that do modify the same object. For instance, if two people in different sessions or virtual machines add different objects to the same set, well, that's clearly not a logical conflict. At the end of both of those, the set has both objects in it now, and it didn't before, and it doesn't really matter which order those happen. The result is the same anyway. So we offer what we call reduced conflict classes that, with an RC prefix on the class name, that automatically handle those kinds of things and let those kinds of operations go through. Now, they're reduced conflict, not completely conflict-free, because some things are actual conflicts. For instance, if you with a dictionary, if you were to add, two people were to add the same key to the dictionary, but with different values. Now that's a conflict, because depending on what order it happens, you'd get a different result at the end. So we've got a lot of different VMs, virtual machines, in what we call sessions, which are the logical views. There's one logical view per session. And we have these persistent objects, but you might not want every object that you have to be persistent. You might not want to share every single object that you're dealing with everyone in every other session. Like, for instance, temporary objects you're using for computation, things you're holding on to for just these particular sessions. So we have transient objects as well. And which objects are transient, which ones are persistent, are defined by reachability. And in Smalltalk in general, and Smalltalk-like languages, the life of an object is determined by reachability from some set of root objects, often a single root object. So that if you can traverse a path from the root object to the object you're talking about, then that object is live. This is the principle on which garbage collection works. If you can't reach the object from any of the live roots, then the object can never be reached, and therefore is garbage. Here we have, in GemStone, we have a set of transient roots, primarily a special array called the session state array that's in the virtual machine. And that's the root for all transient objects, and is only for that session. And then there's a single persistent object, which is the persistent root. And that is the root of all persistent objects. And that's a thing called all users. Another set of transient roots is what's on the stack. Any temporary variables that are on the stack are also considered a transient root. So if you create a new object, it's going to be typically on the stack, therefore it's going to be a transient object. It's going to be around for a while. If that reference to the stack goes away because you've returned from that, then that object could be garbage collected, unless you've made it referenceable from another object. Now, if that other object is a persistent object, and you've got a reference from a persistent object to a transient object, then when you commit, then that object will be found to be reachable from the persistent root, and therefore it will become a persistent object at that point. So that's some of the basics of how GemStone S works. And one of the things that we can do with this is that it can be very large. With a traditional Smalltalk, all of your objects are in memory at once. With GemStone S, because we have persistent objects on disk, and you don't have to have them all in memory at once. You only have to have the ones in memory that you're dealing with right at that moment. So it can get pretty large. We have customers that have repository sizes up in the hundreds of gigabytes. I think about half a terabyte is our largest actual production customer right now. We've tested up to a terabyte, and the architecture should go considerably larger than that. We do have customers that run thousands of virtual machines at once, all accessing the same objects. And we do have customers that are running hundreds of Linux blades, all accessing the same objects at the same time. We have the architecture goes up to about it goes to 2 to the 40th objects, which is roughly 10 to the 12th. We've got customers that are somewhere in the middle, like 5 billion, 5 times 10 to the 9th objects. And we handle rather large collections as well. So we can handle collections of up to typically millions of objects. In order to be able to handle those more efficiently, we do have the ability to put indexes on large collections so that you can find things indexed by various properties of the objects without having to iterate through all the collections to find things, and ways to specify queries on those collections. And all those things help to manage it when your system gets large. Now, it's not that your system doesn't have to be large to deal with GemStone, but it certainly can be. So sometimes you'll hear people say that GemStone S is an object database. And so given everything that I've just told you, do you think GemStone S is an object database? Who has an opinion? You don't count, James. Okay. but I saw another hand there. Yes. You think yes? Yes. I think it's fair to say that GemStone S includes an object database. I don't think it's really correct to say that it is an object database. It's really a Smalltalk implementation. But it is a Smalltalk implementation that includes an object database very, very tightly bound to the Smalltalk implementation. All right, so now if you have all these persistent objects, they can be very, very long-lived. And your, and your data is probably very valuable. Some of these objects, maybe your business data or things that you really, really want to keep around. And your applications, as we know, applications evolve over time. So if you had a relational database, you would be faced with the problem of schema migration, where you need to change what tables you use and that sort of thing. And when you change your object structures in your object application, you have the same issue to deal with. If you've got a lot of persistent objects and you want to change what instance variables they have, you want to add an instance variable to this particular class or something like that, and you've got 340 million of that particular class sitting out there on your disk, and they don't have that instance variable, then you need to deal with how you add that and how you move on. And the way we do that is through migration. So you can add and remove methods from a class very easily, just as in any Smalltalk. But when you change the structure of the class, when you add or remove instance variables, for instance, then there's extra work needed. And we do that through class versions, which sounds kind of scary, but actually each version of a class is really just a class. So what we do is, for instance, if you were to add an instance variable, then we would create a new class with that instance variable. Now, what would happen in something like Squeak would be that to add the instance variable, you add the instance variable and you recompile all the methods, and then you find all the instances of that class, and you mutate them all to be bigger, to have this extra instance variable in them, and you initialize that instance variable to nil throughout, and that happens very quickly, maybe a few hundred milliseconds on modern machines, less than a second usually, because everything's in memory and you can find them all that quickly. Well, when you've got 0.5 terabyte of objects in there on disk, it takes a lot longer than a few hundred milliseconds. It can take hours. It can take sometimes many hours. And so we don't do it that way. So we allow there to be multiple versions of the class coexisting at the same time. And each version is, as I said, is a class. And these classes are linked together by a thing called a class history, which is an ordered collection of versions. And once again, each version is just a class. So I've got a class history object that references two versions, the old version of my class that does not have my new instance variable, and the new version of my class, which does have that instance variable. And each object is an instance of exactly one of those classes. So, so it's not an instance of both versions at once. Now, because the objects the classes are linked together by a class history, I can ask the dreaded is kind of, which we try to avoid using, but every once in a while you need to. You could ask it is kind of, and you can say is kind of either version of that class, and because they're linked by a class history, you will get the answer of true. But it's actually an instance of only one of them. And so what you want to do is you want to be able to migrate those instances from the old version to the new version. And there's a migrate message that does this. And there's a default migration that is already set up for you. You set a migration destination for a given version of the class. So say I'm migrating from this version to this version. Then you can send migrate to any instance, and it will become an instance of the new version of the class. By default, Instance variables are simply copied by name. So if there's instance variables with the same name in the old class version and the new class version, then the values will be copied across. Anything that's new will be, by default, initialized to nil. Anything that is only in the old version will be discarded. You might not want that. Maybe you're changing the name of an instance variable. In that case, you can define a custom migration that says, okay, from the instance variable A maps to the instance variable B in the new one, and it will copy that value across. You could also do more complicated things. You can initialize the new variables to values other than nil, etc., with a custom migration. And often, if you want to do this without taking your system down, you can. It's a little bit, you have to be careful about the sequence of operations. Often, if not all of the instances in your repository have the new instance variable, you're adding the new instance variable because you want to use it, but you can't necessarily use it across the board yet because not all of your instances have it. So often, if not having downtime is important to you, you will gradually migrate all of your instances over to the new, to have that instance variable, and then change your methods so that they start using that instance variable. Another issue that can come up when you're dealing with a multi-user system is security. If you've got a bunch of people accessing the same object, it's no longer a personal system like Smalltalk was originally designed to be. So we have a couple of different levels of security built into GemStone. There is the user level security where you log in. Each user has a username and a password, and you log in using that. And you can't really get access to the system without having some username and password. And what username you log in as gives you certain rights relative to the relative to what you can actually do. So, for instance, there's privileges that go along with each user. There's special privileges in some cases, like the privilege to be able to change code, which you might give to all your developers but not give to your ordinary users. There's privileges that you only would give to your administrators, like the ability to change other people's passwords. That's one that you don't give out to too many people. But there's also object level security. For each object is associated with an object security policy object. So there can be, I think, up to 64,000 object security policies in the system. And for each one of those, you set a policy of who the user is that owns that policy, and for that user and what group it's associated with. And like Unix file permissions, you have read, write, or both, or no permissions to access that object based on that policy for that user and group and for other users. So for each object, you can say only this user can read that object, or only this user can write that object, or only users in this particular group can write to this object, but others can read it, and things like that. And we've got a couple of other things that are unusual in a Smalltalk. Objects in GemStone are variable size. The number of indexed instance variables can be changed at runtime. In most other Smalltalk implementations, things that are variable size, like ordered collections or sets, are based on underlying implementations that are where you have to actually use a different object and use become to replace that object, or it references an array and you replace that array with a larger array when it changes. And we also have a different scheme for resolving global names. In a typical, in something like Squeak, for instance, or Pharo, you have the Smalltalk is the name of the global system dictionary, and everything, all the global names are resolved through that. And and I'm running out of time, so I'm going to go over this fairly lightly. But in GemStone, you've got symbol dictionaries which resolve these variables for you. Each user has a symbol list that's active at any given time. This is an ordered list of what dictionaries to search, and then you can have a series of dictionaries. So all of the classes, for instance, that are part of the kernel that come with GemStone are in a single dictionary called globals, and you can put that in your search order. And you can use this. You can, by omitting a dictionary from from some user's symbol dictionary, you get a little bit of security in that they have trouble resolving that name. That's not usually very tight security. You should probably use the object level security if you really, really care about somebody not accessing something. In the old days, it was useful to have multiple developers sharing the same development repository because the resources taken were fairly large. These days, machines have such capacity that something like this 4-year-old laptop can hold several repositories at once and run them without any problem. So that's not as important anymore. A little more interesting is you can use it for namespacing. That by manipulating your symbol list to be able to search particular things, you can have classes or other variables that have shared variables that have the same name but are resolvable in different ways at different times. So that is most of what I've got to say. We do have, for further information, there are going to be some more talks on GemStone. As you saw, we have invaded, and tomorrow we've got talks from Norm, who's going to talk about the recent developments in GemStone development and what we're planning in the future. And James will talk about the web tools framework that he's been working on, and Dale will be talking about Toad on Saturday to close out the convention. And for more information, there's gemstonesoup.wordpress.com is Dale's blog, and it has quite a lot of information about using GemStone S. And at seaside.gemstone.com, there's hasn't been updated too nearly as frequently as Dale's blog, but it has a lot of information about how to download GemStone S, how to try it out. GemStone S is a commercial product, but there is a free edition that is available for use at no charge, even for commercial use, up to a size limit on the number of cores that you can use it to execute and the amount of memory. But I think otherwise unlimited these days. So that's a lot of people are using that, and it's a pretty good thing to get started with. Certainly talk to any of the GemStone people that you see here this week. And I think we have just a couple of minutes for questions. Yes?
Hi, I'm very good.
Okay, there's a microphone coming.
For example, at what time you detect the conflict between objects and the commit transaction message or in the middle of the first one?
Okay, so you're asking when do we detect a conflict between objects? For a commit conflict, a conflict between the changes I'm making and the changes that someone else is making, that is detected at commit time. There are some other things that are detected, like if you attempt to modify an object for which you do not have write permission because of the object security policy of that object, that will be detected immediately. But the commit, the change between, or the conflict between the changes I make and the changes that someone else is concurrently making, that is done at commit time.
And the second question is, you mentioned hundreds of machines, thousands of VMs, but my object as a user, where resides? Only one, they are duplicated, or they are distributed, but only one is...
Okay, so you're asking where the objects are. Logically, it's all one object. So you can think of it as all one object. Now, the way it's implemented is there is an object on, it lives on disk somewhere that the shared state of that object is. But each VM that is actually accessing that object or dealing with that object, sending messages to it, will have copied that object into its own local memory of that process. So that one object will be copied into local memory as you use it. So it's basically on demand. Those things are faulted into memory.
One question about architecture. You talk about VMs. My question is how the scaling is made. I mean, when you want to grow up on VM count or maybe reducing because you are starting objects, you need less VM to do the same work.
Right.
Just in a big picture, how is it made? Scaling?
Okay, so scaling in terms of number of virtual machines. It depends on the architecture of your application. Many of the older applications, many of the existing applications out there are applications that are from a desktop using the GemBuilder for Smalltalk. So then, in that case, there is usually for each person who is logged into to the system, there is one virtual machine on the server for each user. So that's the existing model. Now, for a web model, it's going to be different, and that is there is more. Dale, do you have anything to say on that quickly?
Yeah, basically So in the web model, what happens is you've got the set of VMs are each VM is going to be handling a request at a time, and so what you have is your web server distributing requests, round-robining requests to a pool of VMs that you've got running. And each one of those VMs can handle any set of requests. So like in Seaside, even though the Seaside model has shared session state, that session state is actually persistent, and therefore any VM can serve any request. So there's no session affinity. So basically where this gets down to is you just continue adding VMs to meet your demand. And the object model is shared across all those VMs, all right? And so you run into practical limits, okay? If you're sharing lots of data, the number of VMs, you start running into limits like shared memory, or possibly your network connections to the database will get hot, all right? But if there's small objects, or small sets, you can go very high. All right, I've run 7,000 requests per second in experiments on 70 CPUs or something like that. So,
yeah.
So there's quite a bit of scaling for the
All right. And if you're interested in the mechanism, the way you add VMs is basically through a shell script, and the way you reduce VMs is the same right now. So right now it's a manual shell script kind of process. Right, essentially, yes. And I believe we are out of time right now, but.
We'll give you 2 minutes.
Okay, so.
2 minutes we have.
Okay.
And I have a question for you.
Okay. Now, I'm going to, oh, Andres has. Andres has a question. I'm going to hide under the desk. Okay.
You asked a question to the audience of whether GemStone was an object database or not.
Yes.
And in the sense that, and I get the idea from what you're saying, that in the sense that GemStone provides a shared image to other small images, it is not a database. But at the same time, I use GemStone in practice, and I know that it's a database. So, what do you think?
Yeah. Well, as I said in the talk, I think GemStone, GemStone is a Smalltalk implementation first, but it's a Smalltalk implementation that has an object database as part of it.
Yeah. So I decided to add
In what? Anyway, maybe looking for something subtle.
Yes. GemStone is more than an object database. How about that? Does that any more satisfying?
We can sell it as a database and more.
Yes.
What happens when you share the implementation with Multiuser?
What happens when you share the database, the object database with Multiuser?
With what? With
Maglev.
Oh, with Maglev. Ah, yes. Well, that is a topic that that's interesting. We have, for those of you who may not know, we also have over the last several years implemented Ruby on top of that. So now GemStone S also, with the maglev layer on top of it, also runs Ruby in the same system and in the same VM. So we have Ruby and Smalltalk running in the same VM and sharing the same persistent object repository. And because the object model is similar enough, that works pretty well. And at the ESUG conference a couple of months ago in Scotland, I gave a presentation on calling Ruby gems from Smalltalk, and that works pretty well and can be done. But well, no, it's Ruby execution. Yes, you can store Ruby objects as well, but yeah. Okay. All right, now I think we really are out of time. So
Actually, give me more than 2 minutes. So anyhow, thank you.